Hello everyone. In this video, I'm going to walk you through the basics of running regressions in R. So first up, I'm going to clear the environment, and then I'm going to load some libraries that I need. You've already seen some of these libraries, mass and tidyverse. I'm going to run them because I need some functions from there. So this library is specific to the Introduction to Statistical Learning text. So there are some functions that we are going to use from this package. Probably not in this video, but in some of the subsequent videos. And this text and this package also has some data sets that we will be working with. So I'm going to load this library. If you haven't loaded it yet, you need to install the library. I'm going to load tidyverse, and I'm also going to load this package called estimator, estimator. This is for running heteroscedasticity robust standard errors. So make sure you have all the packages installed first before you run these regressions. So for this example, I'm going to work with this data set called Boston that has some housing data for suburbs of the Boston area. So as you can see, there's these variables: crime, zone, industry, RM, age. These are these different variables that we're going to work with. Sometimes it's often useful to attach a certain data set to the temporary memory, and this code is straightforward. Just attach and then within parentheses write the name of the data set. What this does is that it eliminates the need to keep typing the name of the data set when you want to write the variable. So in a lot of data frameworks, you can see them following this template: the name of the data set, $, the variable. If you have a certain data set attached to the memory, you can simply write the name of the variable and you should be good to go. So that's one advantage of using this command. So now we are going to run some regressions. First up, I'm going to regress a single variable model. So one predictor and one predictor and one response variable. And my dependent variable is med_v, which is a median value of owner occupied home, and lstat is my predictor variable, which is a percentage of lower status population. I run the regression, I store the results in the object called lm_fit, and you can see that the model is ready. If I want to print the basic information, I can just type in the name of the object and execute, and it will give me the point estimates. So my estimated beta hat over here is negative 0.95. But if I want more information, I need to run the summary command. So summary and then lm_fit, and it will give me all the other informations as well. So I'll get the beta hats. I will also get the standard errors, t statistics, overall significance, and everything. If I want to extract just the coefficients of a model, I use the coef function. So coef function recalls the point estimates that are there in this model, which in this case is the intercept and the lstat. If I want to extract a 95% confidence interval, I will use the confint function. So these are the confidence intervals for lstat variable, which is from negative 1.02 to negative 0.87. If I want to predict the median home values based on this model, I will use the predict function. If I want to extract the prediction intervals for lstat values at 5, 10, and 15, the code remains the same, just the interval changes. So I'm just tweaking the code over here. Everything else remains the same. I want to plot the relationship between lstat and med value. So I use the plot function, and you can see that this is the relationship that these two variables have with each other. I want to run the regression line through this. So the command is this. So you use the app line command. Inside the app line, I fit the model that I have that I have regressed, and then I fix the width of the line and the color of the line. Next, I want to add some more plots to this. So suppose I want to run some diagnostic plots for the linear model. First, this line over here sets up a 2x2 grid plots for diagnostic plots. So I'm basically setting up my canvas where the lines, like where the figures will get implemented. And then if I run the plot command and just fit in the model, it will automatically give me a lot of very useful diagnostic figures. So I have a plot where I'm seeing the residue, where I'm plotting the association between residuals and the fitted values. I have the QQ residual plots. I have some scale location as well as residuals versus leverage. Leverage is when leverage captures how influential a particular observation is in a data set. So that's what is happening over here. It's very useful and gives you a quick look at whatever things are happening. Next up, I want to increase the number of predictors in the model. So the template remains the same. Med value, tilde, and then I just add all the variables as with the addition sign. Now I've typed data equals Boston over here, but I did not necessarily have to do that here because I've already attached the data set. But if you don't want to do that, then you need to also specify the data set in any general regression function. And just to be clear, LM over here stands for linear model. So once I have the model, I look at the summary of the model. So now I have a regression with mid value as the dependent variable, LStat and age as the covariates, and these are the point estimates, these are the standard errors. So I have the full regression table now. There are a couple of cheat codes over here. So suppose you want to run a multiple regression model using all variables except the one that is there in the independent variable. What you can do is, instead of writing out all the names of all the variables, you can just type in dot, and R will understand that you want to regress med value on all the other variables. And you summarize it. So all the data set, all the variables that are there in the data sets have now been included as predictors. I load the car package for some additional regression diagnostics. I want to check for multiple linearity using the VIF. The command is straightforward. Just type in VIF and writing the name of the model. As you can see over here, the VIF number for both the predictors is less than 5. So there is no evidence of multiple linearity. Suppose I want to tweak the model and add an interaction term between LStat and age. This is what I do. So I type LStat, age, add an interaction between that. So now you have the mean effect of LStat, mean effect of age, and an interaction between LStat and age. So this is how you do it. You want to add a quadratic term for LStat. There are several ways you can do it. The easiest way would be to add LStat and then use this I function inside which you type in a function of LStat. So this is a quadratic model in LStat. And if I want to compare this with the original model, So this is the linear model where the point estimate of LSTAT was negative 0.95. And this is a quadratic model. You see the mean effect is now different. Earlier, the point estimate was just negative 0.95. Now it is negative 2.3 for the mean effect, and the quadratic term has a positive 0.04. Interpreting these coefficients is different, so be very careful about which model you are fitting in and what you are trying to accomplish. You can also do it in another way using the poly function. So instead of suppose I want to create a polynomial in LSTAT. So I type ln parenthesis mid value and then all 5 orders of the LSTAT variable. So now I have two different things. This is an easier way of doing it because we need to write less. So this is the linear term in LSTAT. This is the quadratic, this is the cubic, then to the power 4, and then to the power 5. So for the rest of this code, I'm going to use a different data set from the ISLR2 package. So we are going to use the car seats package that has information on car ownership. And I'm going to fit a linear model where I'm regressing the sales of car on all variables, and I'm also including an interaction between income and advertising, as well as an interaction between price and fee. But the issue is that there can be some potential problem of heteroscedasticity. So what we are going to do is that instead of using the general ln function, we are going to use the ln underscore robust function, which is from the estimator package. We are going to run a simple model, fix the data set, and then specify the type of heteroscedasticity that we want to adjust for. HC1 is a standard one that we will be using for this course. So this is a heteroscedasticity robust standard error. So I stored the standard errors in the variable called standard errors R. I run the same model, but now I do not account for heteroscedasticity, and I store it in a vector, and I print the standard errors to compare. Look at the standard errors over here. So if I don't account for heteroscedasticity, my standard error for the LSAT variable is 0.038, whereas if I account for heteroscedasticity, my standard error is actually larger. So by not accounting for heteroscedasticity, I'm actually overestimating the precision of my estimates. Then I'm going to talk about the difference between R squared and adjusted R squared. So I'm going to use the simple empty cars dataset that is preloaded in R, and I'm going to run a bunch of codes, and I'm going to print the results. What I'm doing is that I'm adding more and more predictors that I think are relevant, and I'm going to compare how R squared changes with how the adjusted R squared changes. And as you can see, the red dots are how adjusted R squared changes, whereas the blue dots are how the normal R squared changes. Note that as I add more and more predictors, both R squared and adjusted R squares are increasing. But adjusted R squared is always lower than R squared because it is accounting for the fact that you're making the model more complex by adding more predictors. So it is penalizing the goodness of fit proportionally. But I think the best way to look at this is by having a regression and then adding jump variables to it. So I'm going to add 5 totally random variables to this data set, and I am going to rerun this exercise and see what happens. So as you can see, so if you compare these two, so as I add more and more variables, my R square is increasing even though I'm adding junk variables, but my adjusted R square is decreasing. And that is what you see over here. A part of it has been hidden by this legend over here, but if I remove this line, so if I remove these lines and run the code again, so look at this figure over here. As I'm increasing more and more junk variables, my R square is increasing, but my adjusted R square is actually declining. So I'm fitting a worse and worse model by throwing in more junk variables into the system. So this is why we almost always prefer adjusted R square over R square, because it allows us to truly evaluate whether we are actually making the model better by adding an extra variable. So this is the basics of running linear regressions in R.